Picture a gleaming R&D lab at a major tech company. A team of engineers has just perfected a revolutionary new motor for an electric vehicle. It's smaller, more powerful, and more efficient than anything on the market. The secret is a tiny, hyper-powerful magnet. They've already secured a steady supply of the necessary rare earth elements from a partner overseas. Everything is a go for production. Then an urgent memo from the legal department comes through. It's a bulletin from China's Ministry of Commerce. As the project lead reads it, the celebratory atmosphere in the room just dies. The problem is no longer about the raw materials. Beijing has just declared that the technology itself, the specific know-how for smelting the metals, for manufacturing those exact high-performance magnets, is now a controlled export. Suddenly, it's not enough to have the ingredients. You now need to apply for a license just to use the recipe. A recipe that originates in China, even if the factory is in another country. And a chilling line near the bottom makes it clear that any application tied to producing high-end semiconductors will be scrutinized, case by case.
That breakthrough motor and countless other critical tech projects have just been put on an invisible leash held by Beijing. Welcome to the deep dive. That opening scenario, well, it's the new reality for global high-tech manufacturing, isn't it? For years, we've all been focused on, the geopolitical risk of rare earth elements, the actual raw materials.
Right, the stuff you dig out of the ground.
Exactly. But our mission today is really to dissect this profound pivot. We're talking about the shift from controlling the earth, the minerals themselves, to controlling the mind.
The mind, meaning technology.
Yeah, the technological know-how, the intellectual property, the industrial processes.
Yeah.
Basically the recipe for making things like those high-performance magnets or doing advanced processing.
And what's really fascinating here, I think, is that this is a far more sophisticated strategy. It's much more long-term than just, say, slowing down a shipment of raw ore.
It feels different, yeah.
These new stringent export controls, they fundamentally redefine the global supply chains for critical components, stuff used absolutely everywhere, from EV motors to, advanced AI accelerators.
Right.
This isn't about hoarding materials anymore. It seems much more about securing long-term technological leverage. So we're exploring what these controls actually entail and why they matter so much for the future of, well, any nation trying to secure its own industrial capability.
Okay, so let's really unpack this. Let's start with the rules themselves, the sort of cold, hard facts that define this new technological barrier. We need to understand the scope of control first, because it feels like a really significant expansion.
It is. It moves well past just controlling, say, raw elements like gallium and germanium, which we saw restricted earlier. Now it's really encompassing intellectual property, specific industrial processes.
How to.
Precisely. This policy looks like a comprehensive defense of the entire rare earth value chain. The scope now reaches deep into what we call the industrial midstream.
The processing stage.
Exactly. These restrictions explicitly cover technologies related to mining, smelting, separation, making the magnetic materials themselves, and this is significant, the recycling of rare earth secondary resources too.
So the whole life cycle.
It's a full spectrum defense, it seems, of the intellectual foundation that underpins their industrial dominance in this area.
What really struck me was how specific they got about the actual machinery, the production lines themselves. It's not just regulating the output or the IP on paper.
No, it's regulating the physical tools used to execute the process.
Which seems like the key leverage point, doesn't it? Especially if you're trying to diversify production outside China.
That's exactly it. That's what complicates any future diversification effort. The restrictions explicitly cover the assembly, adjusting, maintenance, repair, and upgrading of production lines related to these rare earth technologies.
Wow, so maintenance too.
Yes. Think about what that means in reality. If a foreign company operating outside China uses specialized processing equipment made in China, or maybe even just licenses a proprietary Chinese process.
Which happens a lot, I imagine.
Absolutely. They might need permission just to maintain or upgrade that equipment if a critical part breaks or there's a new software patch needed to boost efficiency.
Suddenly your whole operation could grind to a halt.
Potentially. Or at least it becomes reliant on Beijing's approval to keep running optimally.
That dramatically deepens the dependence, doesn't it? It shifts the risk from, can I buy the raw materials, which was the old question,
right,
to can I even maintain my factory's ability to operate efficiently? And if I can, is my factory now running on Beijing's timetable?
Exactly. And you have to look at the market share here. While China accounts for maybe 60% of global rare earth mining,
which is a lot, but not total dominance.
Right. The crucial choke point, the real bottleneck, is the midstream refining. They account for approximately 90% of processed rare earth output globally, and about the same for permanent magnets.
90%.
90%. So this new shift, focusing on the technology, it ensures that even if Western nations manage to find and extract new deposits of rare earth ore somewhere else,
Like in Australia or the US.
they could still remain technologically dependent on Chinese know-how to actually turn that raw ore into the highly refined metal or the specific component that an EV motor, for example, actually requires.
Okay, let's talk about this global licensing requirement, the thing we call the invisible leash in the intro, because that seems to apply even to stuff made outside China, which sounds incredibly complex.
It is perhaps the most far-reaching and maybe the most complex element of this whole new regime. Yes, the rule applies immediately if you're exporting rare earth products made in China. That's straightforward enough.
Okay.
But the really game-changing part, the truly stringent requirement, is that products manufactured overseas are also subject to these controls if they include elements or use technologies that originated in China.
Okay, hold on. How is that even tracked? There's that tiny percentage trigger you mentioned.
There is, and it's almost impossibly low, which makes tracking incredibly difficult. If the Chinese originated components or the technology, maybe the IP embodied in a specific processing method, make up just 0.1%, 0.1% or more of the value of the finished product manufactured overseas.
0.1%.
Yes. Then the exporter, wherever they are, must apply for a dual-use item export permit from China's Ministry of Commerce.
How on earth does a global company audit that? We're not talking about tracking a major component like a chip that's 5% of the value. We're talking about tracking the fractional value of a specific, maybe licensed chemical process used like 3 steps upstream in the supply chain.
Exactly. For a component that then goes into your final product.
That sounds like a compliance nightmare.
It creates an enormous compliance headache. Let's take an example. Imagine a German automaker.
Okay.
They use advanced magnetic components, maybe made in Malaysia. Now, that Malaysian factory might source its refined rare earth metals from a non-Chinese mine, let's say.
Right, they've diversified the raw material source.
But maybe they use a specific proprietary solvent extraction process that was originally licensed from a Chinese metallurgical firm, maybe decades ago.
Which could easily happen.
Very easily. Now, if the value attributed to that licensed process, the IP value exceeds that 0.1% threshold for the final value of the car.
Not the component, the whole car.
The finished product manufactured overseas, then theoretically, that German automaker needs to apply for an export permit from Beijing just to sell that car globally.
Wow.
This regulation essentially forces global manufacturers to conduct deep-tier supply chain IP audits to figure out the origin and value contribution of licensed technologies deep in their supply chain. That's, well, it's a new and pretty unprecedented requirement.
The granularity and the sheer reach of that are just staggering. Okay, so moving past general manufacturing, these controls also seem to zero in on specific high-stakes industries for extra scrutiny. They're not really hiding their targets here, are they? Especially when it comes to tech competition.
No, not at all. The language is quite clear. While the controls state that export applications involving military end users will, in principle, not be approved, which is fairly standard for dual-use controls,
Right.
the detailed attention given to advanced semiconductors is equally, if not more, revealing. It tells you a lot about their economic and strategic priorities.
So what's the specific technical line they're drawing in the semiconductor world?
Okay, so applications related to advanced semiconductors are specifically flagged for rigorous case-by-case approval. And this scrutiny targets R&D and production of logic chips at 14 nanometers and below.
14 nanometers. That's kind of the threshold for modern advanced chips, isn't it?
Generally, yes. It's often seen as the boundary between older, mature technology and the current leading-edge production nodes that power things like modern data centers, AI systems, high-end smartphones.
And it's not just logic chips.
No. They also target R&D and production of memory chips, specifically 3D NAND flash memory at 256 layers and above. Again, that represents the cutting edge of density for memory.
And the regulatory eye looks even further than the finished chip itself, right? It goes to the tools.
Absolutely. And this is critical. The controls explicitly include the manufacturing or testing equipment and the materials used for these advanced semiconductor processes.
Ah, so it connects back to the rare earth materials themselves.
Precisely. It confirms they understand the choke points across the entire ecosystem. By controlling the technology needed to refine certain rare earth materials to high purity, they are, in effect, controlling the quality and supply of essential components or chemicals that go into the specialized equipment that makes the most advanced chips.
So you could see this as a preemptive move, managing the supply of crucial inputs to the very cutting edge of the global chip industry. It really highlights how central these critical mineral processing technologies are and their dual-use nature.
It certainly does. And we should also note they apply that same rigorous case-by-case approval to exports intended for R&D of artificial intelligence, specifically AI with potential military applications.
Right.
Taken together, it confirms that these controls seem strategically positioned. They appear designed to protect hard-won intellectual property that's seen as crucial for achieving their national goals of, indigenous innovation and building a sovereign, robust industrial capability.
That leads us perfectly into our next section, Section 2. We need to understand the strategic drivers behind this whole shift, because often when we hear about these controls in international media, the framing is almost solely about geopolitical leverage, right? Using resources as a weapon.
That's usually the headline, yes.
But we need to address the other arguments being made, especially the ones coming from within China, particularly around sustainable development and protecting that hard-won, expensive IP.
Absolutely. If you look at the publicly stated rationale and the internal narrative that seems to be emerging, these controls are positioned very strategically for long-term goals. Goals like sustainable development and safeguarding critical technological advancements they've made.
So less about short-term tactics, more about long-term strategy.
It appears so. The policies are often explicitly aimed at fostering indigenous innovation, achieving technological self-reliance, and building a robust national industrial ecosystem. And importantly, an ecosystem that's also cleaner and more efficient than what existed before.
That's an interesting angle. Moving beyond just market control to securing a cleaner, more refined industry model. That often gets lost, I think, in the typical narrative of resource competition.
It does, and there's a perspective apparently from a scientist working in Gansu that really illustrates this link between the historical environmental cost and the current value placed on the IP.
Gansu.
Yeah.
That's a major rare earth hub, isn't it, historically?
A critical one, yes, in southern China. But it's also a place with a significant environmental legacy, tied to the earlier, frankly, quite messy extraction methods used decades ago.
Like the acid leaching.
Exactly. Those processes often involved huge volumes of acid, leading to widespread groundwater and soil contamination. They literally left behind mountains of polluted residue. It was environmentally damaging.
That was the price paid, essentially, for pioneering the modern global rare earth supply chain that everyone now relies on.
That's one way to look at it. And according to accounts from environmental scientists working there now, the new technology development, things like proprietary, cleaner separation techniques that use much less acid, require less water, produce cleaner byproducts, this is viewed almost as a national mission.
A mission to fix the past problems.
In part, yes. These new technologies represent massive investment, decades of research, specifically aimed at transforming that legacy of environmental damage into something sustainable.
So for the current generation of innovators and engineers there, they see this new tech as the solution to the historical pollution problem. And the export controls on that specific tech are about protecting the IP that made the solution possible.
That seems to be the core argument from that perspective. It's like saying, look, we paid the environmental price back then. We made the huge investments, billions in R&D to innovate and clean up this industry. Now we're going to protect the intellectual property that ensures future development is both sustainable and profitable for us. We want to build a future that's high-tech and green.
That certainly reframes the motivation, doesn't it? It suggests protecting this IP is as much about environmental stewardship and future resource efficiency as it might be about maintaining global leadership or leverage.
It adds another dimension to the story, absolutely.
And this focus on controlling technology, it isn't just happening with rare earths as isolation, is it? It seems to fit a broader pattern we're seeing across other critical mineral processing sectors, like a unified strategy to control the midstream IP.
That's right. If you want evidence of a potentially unified strategy, you just need to look at battery chemistries, specifically lithium iron phosphate, LFP.
Which is huge for EVs now.
Becoming dominant, yes. And we've already seen proposed export license restrictions bubbling up around technologies related to making LFP cathode material, and also lithium processing more generally.
And this is another area where China holds a strong position.
a dominant position. They hold a significant majority of the patents around advanced LFP materials. We're talking about the newer stuff capable of faster charging, higher energy density, and also critical pack-level innovations like cell-to-pack integration, which reduces weight and cost.
And just like with the rare earth tech controls, are the proposed LFP restrictions also very specific, technically?
Extremely specific. They apparently target technology for making LFP with a specific tap density of 2.58 grams per cubic centimeter or greater.
Okay, that sounds very technical. Why is that density figure important?
Achieving that density isn't easy. It's a sign of advanced material processing. It basically defines the recipe for advanced fourth-generation LFP materials. If your LFP material doesn't hit that density, it limits how much energy you can store and how quickly it can charge.
Ah, so it affects the battery's performance directly.
Directly. So by potentially controlling the technology that allows manufacturers to consistently hit that specific density threshold, they could effectively lock down the performance specs of the most rapidly growing segment of the global EV battery market.
So again, it's not just about controlling today's standard products or the raw lithium. It's about controlling the next generation of materials and securing a technological advantage for the next decade or more.
Absolutely. And that technological leverage extends even further right to the very end of the product life cycle.
Recycling.
Recycling, too. Yes. This feels like the ultimate move towards creating a closed-loop system, ensuring long-term sovereign industrial capability. China already controls over 80% of global battery recycling capacity. That includes both the complex pretreatment stages and the actual material recovery.
And didn't you say the new rare earth technology controls now explicitly mention recycling?
Correct. They specifically include recycling of rare earth secondary resources. And this is crucial because, think about it, over the next decade or so, the global feedstock for rare earths is going to shift significantly.
Away from just newly mined ore.
Yes. Increasingly towards manufactured scrap from magnet production and eventually a huge wave of end-of-life EV batteries and wind turbine generators.
Right, the circular economy aspect.
Exactly. So by including recycling technology in the controls, China ensures it maintains technological leverage over the entire circular economy for these critical minerals. If someone develops a new, super efficient, patented method for recovering, say, dysprosium from retired magnets.
That IP is now potentially covered by these export controls.
Under this regime, yes. It solidifies control over the full life cycle and potentially locks in future supply security, even as the world tries to rely more on recycled materials.
Okay, let's shift gears slightly into Section 3. Let's explore the more immediate global implications of all this, particularly for what might be the most sensitive high-tech sector of all, advanced semiconductors. We know rare earths are vital for magnets in EVs and wind turbines, that's clear.
Yeah.
But how do these materials directly impact making high-precision computer chips?
This is where the risk becomes truly systemic. Because rare earth elements, REs, are crucial for multiple, often non-negotiable stages in semiconductor manufacturing. It's not just indirect, like powering the factory equipment.
Okay, so what are the direct roles?
Well, let's look at a couple of key ones. First, elements like neodymium and dysprosium, the same ones used in powerful motor magnets, are also essential for making the high-performance, high-temperature magnets used within the manufacturing equipment itself.
Like in the machines on the production line.
Exactly. Things like sophisticated robotic wafer handling systems, specialized vacuum pumps needed for the ultra-clean room environments. These magnets are critical for the precision and stability required in the fabrication process.
Okay, so that's an equipment dependency. But you mentioned chemical reliance, too. That sounds even more critical.
It is. The chemical requirements arguably represent the ultimate choke point. Take cerium oxide, CEO2.
Cerium, okay.
Cerium oxide is absolutely vital for a process called chemical mechanical planarization, or CMP.
CMP. That's polishing the silicon wafers, right?
Exactly. It's the process where the silicon wafers are polished down to achieve a perfectly flat, almost mirror-smooth surface before the next layers of circuitry are added using lithography.
And why is that perfect flatness so absolutely critical for the advanced chips?
Well, think about the scale. For the most advanced nodes, those 14-nanometer chips, and below that we talked about the features being etched onto the wafer, are incredibly tiny. atomic scale almost. Even microscopic surface imperfections can completely ruin the lithography process, causing defects.
So the light patterns get distorted.
Precisely. For the advanced lithography techniques like deep ultraviolet DUV and especially extreme ultraviolet EUV to work properly, you need sub-nanometer flatness across the entire 300-millimeter wafer. It's an incredible engineering challenge.
And cerium oxide is the key to achieving that flatness.
High-purity cerium oxide slurry is the material of choice for this precision polishing. It has unique chemical and abrasive properties that allow it to gently remove material and achieve that incredible smoothness without damaging the underlying silicon. Basically, if you can't get the right quality high-purity cerium oxide.
You can't do the CMP effectively?
Right. And if you can't do the CMP, you simply can't make the most advanced chips, period.
That makes the risk incredibly tangible for the big global chip fabs, doesn't it? They're reliant on REEs not just for magnets somewhere in the building, but for the actual chemical materials used in the core process flow.
And cerium's just one example. Other rare earth oxides like lanthanum oxide, Le2O3, and yttrium oxide, Y2O3, are being actively explored and in some cases already used in what are called high dielectric materials.
IK.
High dielectric constant. They're used to replace the traditional silicon dioxide layer in the tiny transistor gates on a chip. As transistors keep shrinking, engineers need materials that can insulate better in thinner layers to prevent leakage.
So the chip doesn't short out or use too much power.
Exactly. And certain rare earth oxides fit that bill perfectly. So, by explicitly targeting advanced semiconductor end users in these export controls, it looks like a way to place a potential technical constraint, not just on current production, but on the entire future roadmap of chip innovation that relies on these advanced materials.
And we absolutely have to place these rare earth technology controls within the broader context, right? This isn't a one-off move by China regarding strategic materials. It feels like part of a trend of tightening export restrictions on dual-use minerals over the last few years.
It absolutely seems to be part of a coordinated or at least consistent strategy. Remember, we saw the controls placed on gallium and germanium exports, particularly targeting the U.S., starting back in December 2023.
Right. Those are key for certain types of semiconductors, high-efficiency solar cells.
Correct. Dual-use items. And that was followed by announcements of subsequent controls on other materials like tungsten, tellurium, bismuth, indium, molybdenum. Those are reportedly scheduled to come into effect in early 2025.
It feels like the strategic emphasis is heavily focused on these relatively small, often quite opaque mineral markets where the supply chains are maybe less flexible.
That seems to be the vulnerability that's being leveraged, yes. These aren't bulk commodities like iron ore. Supply is often concentrated, inelastic, and disruptions can quickly cascade and potentially paralyze complex, high-tech manufacturing globally.
Which is why these controls, across multiple minerals and now crucially focusing on the technology, are forcing the international community to react, to try and accelerate diversification efforts at a scale we haven't really seen before.
The reaction is definitely significant.
So what kind of response are we seeing globally? In terms of policy, actual financial commitments, because the sheer amount of public money being thrown at this problem seems to reflect how seriously governments are taking the supply chain risk.
It's massive. You're seeing a kind of dual response. On one hand, international industries are, perhaps cautiously, trying to engage in deeper technological cooperation or find sustainable resource strategies with China. But simultaneously, governments worldwide are intensifying efforts, pouring public funds into securing critical supplies domestically or with allied partners.
Can you give some examples of the scale of that funding?
Sure. Look at Australia. They've been quite proactive. They've committed substantial funding through big initiatives like their AUD 15 billion National Reconstruction Fund and a dedicated AUD 4 billion critical minerals facility.
And is that money flowing to actual projects?
Yes, definitely. For instance, they've specifically allocated a huge chunk, AUD 1.7 billion, to a company called Iluka Resources. The goal is to build Australia's first fully integrated rare earth refinery, trying to cover the whole process from raw concentrate to refined oxides domestically.
Closing the midstream gap.
Exactly. They also provided AUD 200 million for another project, Arafura Rare Earths, which is building a processing facility in the Northern Territory. The clear aim is to build out a sovereign, non-Chinese supply chain capability.
And the United States. Similar focus on trying to jumpstart its own midstream processing, moving beyond just mining the ore at places like Mountain Pass?
Yes. The U.S. is using a mix of tools. Executive orders trying to expedite the notoriously slow permitting processes for mines and refineries, and direct funding, often channeled through agencies like the Department of Defense treating this as a national security issue and the Export-Import Bank.
Specific examples there.
Key examples include financial support for MP Materials, the owner of the Mountain Pass mine, specifically to help them construct a rare earth magnet plant downstream in Texas, trying to connect the dots from refined oxide to finished component within the U.S., and also funding for Leash Rare Earths, an Australian company, to build a heavy rare earth separation facility in the U.S. Again, the focus is squarely on building domestic, or at least partner country, refining and manufacturing capability to counter that reliance on Chinese processing know-how.
And Europe's trying something similar with its Critical Raw Materials Act, the CRMA.
Right. The EU is attempting to fast-track its way towards reduced dependency. Under the CRMA, they've designated, I think, 47 projects across various critical minerals as strategic.
What does strategic mean in practice?
Faster permits.
Funding.
Primarily faster permitting and potentially easier access to finance. It's intended to streamline the regulatory hurdles and help meet some really ambitious goals they've set for 2030. They want 10% of the EU's consumption of strategic raw materials to be extracted within the EU, 40% to be processed within the EU, and 25% to come from recycling within the EU.
Those are ambitious targets.
Very ambitious. So everyone is clearly trying to finance their way out of this deep dependence, but that brings us right to the uncomfortable truth, doesn't it?
The uncomfortable truth being the focus of our final section, section 4, which is why this technological control, this focus on the know-how, might be the ultimate, perhaps non-negotiable choke point.
Exactly, because despite all this political will, despite the billions in public funding being announced, the actual progress in diversifying the crucial midstream refining capacity, well, it has been incredibly slow. Painfully slow, in fact.
Slower than the mining diversification.
Much slower. This is what we're calling the concentration conundrum. The actual data tells a pretty sobering story. Between roughly 2020 and 2024, the geographic concentration of refining capacity, the processing step, actually increased for almost all critical minerals. That includes rare earths, nickel, cobalt.
Wait, it increased? So diversification is moving backward in the midstream.
In terms of market share concentration, yes. Despite all the announcements of new projects, China's dominance in the refining stage actually grew stronger in that period for many key minerals.
So even with all the political momentum and the funding flowing, China still supplies something like 80% of the world's refined rare earths. And similar for battery-grade graphite.
That's broadly correct, yes. Around 80% for refined rare earths, maybe even higher for battery-grade graphite globally.
Why? Why is it proving so difficult if the will and the money are there?
Because diversifying the mining stage alone isn't enough. Not even close. You can have diversified sources of raw materials, take lithium, for example. You have significant hard rock mining in Australia, brine operations in South America, quite diversified at the mine level.
Right.
But still, something like 95% of the processing of that lithium mine concentrate, turning it into battery-grade lithium chemicals, still takes place in China.
Yeah.
That processing step remains the critical bottleneck. And these new technology export controls seem designed specifically to reinforce China's dominance over that bottleneck.
Okay, so why is it so hard for these new, often heavily subsidized refining projects, the ones the US and Australia and Europe are funding, to actually get built, ramp up, and compete successfully against the established Chinese producers? What are the barriers?
There are really three big compounding barriers: financial, technical, and operational. First, the financial hurdle. Building these complex chemical processing plants is incredibly expensive, and the capital costs for new projects in diversified regions, say North America or Australia or Europe, are typically estimated to be around 50% higher than for equivalent capacity built by incumbent producers in China.
50% higher. Why such a big difference?
It's a combination of factors. Stricter environmental regulations in the West are a big part of it. New Western facilities have to build in, from day one, much more expensive, state-of-the-art pollution control and waste management technologies to address the very environmental issues, like water contamination, that plagued earlier Chinese operations.
So Western projects have to internalize the cleanup costs up front, costs that the legacy Chinese facilities either optimized over decades or perhaps addressed differently under past regulatory environments.
That's a fair way to put it. Plus, the established Chinese producers benefit enormously from decades of sunk infrastructure costs, huge economies of scale, highly optimized supply chains, and logistics. All things a brand new entrant simply cannot replicate overnight.
And that cost gap makes it hard to compete on price.
Extremely difficult.
Yeah.
Especially when you add in market volatility. China has the capacity to potentially flood the market with lower cost product if a new international competitor starts to gain traction, making it very risky for private investors without significant government backing. Hence, all the public financing we're seeing.
Okay, so that's the financial barrier. But even if a project gets the funding, you mentioned a technical barrier, the know-how itself.
Yes, and this is where these new export controls could really bite. Refining rare earths or producing high-purity battery chemicals requires incredibly complex chemical engineering. It often relies on proprietary solvent extraction methods, precise temperature and pressure controls, specialized catalysts.
It's not simple stuff you can just learn from a textbook.
Not at all. These processes are often closely guarded trade secrets, the recipe we started with. And frankly, Western nations have, over the past few decades, lost a lot of the readily available, skilled metallurgical engineering workforce and the practical operational expertise in these specific types of complex chemical separations. That expertise was effectively consolidated in China, along with the production capacity.
So, even if the US or Australia manages to build the physical refinery, they might struggle to find enough people who truly understand the incredibly nuanced, complex chemical adjustments needed day to day to efficiently separate, say, 17 different rare earth elements from each other with high yields and purity.
It's a significant human capital choke point. And the technology controls, by potentially restricting access to licensed processes or even just the ability to easily upgrade Chinese origin equipment, ensure that the practical ability to optimize and scale those proprietary processes efficiently remains firmly concentrated.
Meaning, your brand new, multi-billion-dollar Western refinery might end up running at only, say, 50% of its theoretical efficiency, or producing a lower grade, less valuable output compared to established Chinese competitors.
That's the operational risk. That operational hurdle, the difficulty in matching the efficiency and cost-effectiveness of the incumbents due to know-how gaps, is a key reason why diversification in the midstream remains so slow despite all the political will.
And looking ahead, even factoring in all these massive international diversification efforts currently underway, what do the market projections show for the next decade or so? Are we still likely to be facing this concentration issue?
Yes. The projections are fairly consistent on this. Despite the global race to diversify mining, finding new ore bodies in places like Australia for rare earths, Argentina and Chile for lithium, Africa for cobalt, China is projected to remain the dominant refined supplier for almost all key energy transition minerals right through 2035 and likely beyond.
Still dominant in refining by 2035.
Yes. Specifically for rare earths and battery-grade graphite, projections generally indicate China will still supply around 80% of the global refined market by 2035. The needle is expected to move, but only slightly, despite enormous investment elsewhere.
Which means, even if the world successfully digs up significantly more rare earth ore outside of China in the coming years, the technological knowledge, the processing capacity, the know-how required to turn that ore into the high-purity metals and components needed for our high-tech future, that will still be overwhelmingly concentrated in China.
Precisely. This persistent concentration in the midstream really confirms that controlling the process technology, the intellectual property, the operational know-how, the specialized production lines is arguably the ultimate form of leverage over the entire global energy transition and the future of high-tech manufacturing sectors. It looks like the definitive strategic move to secure long-term industrial dominance in that critical mineral midstream.
So, this deep dive has really shown, I think, how the strategic focus has decisively shifted.
Yes.
It's moved from controlling the earth, the raw materials themselves, which was the old story,
Right.
to controlling the mind. The intellectual property, the complex production processes, these new rare earth export controls, particularly the technology aspect, effectively place a kind of invisible, highly technical tariff, not on goods, but on the very knowledge needed to manufacture the next generation of high-performance components. It seems designed to secure their long-term position as the world's indispensable provider of these advanced process materials.
And while the world races, understandably, to find and finance new mines and build new smelters, maybe this deep dive reveals something more fundamental, that the real future trajectory of the global tech supply chain might ultimately be decided not just by geology or by simple market forces,
But where?
but perhaps in the fine print of legal clauses. Clauses governing complex chemical process licenses, proprietary metallurgical patents, and access to the advanced industrial technologies that are required to transform basic elements dug from the earth into the hyper-efficient, high-value machines that will power tomorrow.